red hat. So, and I work on Java. And I think this is about the JDK, or not JDK, the JVM.
Yep, so
yeah. So, working in the middle of the JVM, Java Virtual Machine, with most of the source code technology. Now, this tool at least, and possibly some others, about how you would measure the performance of that, and that's what we're going to hear about. So thank you very much, guys.
Thank you. So, as already pointed out, my name is Omair. This is my colleague Elliot, and today we're here to talk about Thermostat, which is a serviceability tool for Java. Here's a quick outline of our talk today. We're going to talk about why we started this Thermostat project, what the Thermostat project is, how do you get Thermostat, how do you use it, how do you contribute to it, even extend it beyond what we as developers thought it should do. You'll find out what's happening in Thermostat. And finally, we're going to try and share some lessons we've learned while developing Thermostat. Maybe you can. So, the first question obviously is why start this project Thermostat? Why start a serviceability for Java? So let me first get back to the term serviceability tool. Some of you may not be familiar with what a serviceability tool does. I like to use a car analogy. Once you've bought a car, once it's on the road, it needs to take care of service. You take it, you make sure it's working correctly, you make sure all the parts are okay. For software, the situation is somewhat similar, because you don't change the software when it's running. So what you do is you make sure it's running at the way it's supposed to be. And that's what a serviceability tool does. It allows you to look inside, see if it's behaving the way you design it to behave. It's sort of a sanity check. So there are several aspects to this serviceability tool, Thermostat. I'm going to go clockwise. So first of all, we want this open source serviceability tool that should work on OpenGL and Linux. Of course, it should work on other architectures too, but the prime ones are open source platforms, which currently OpenGL and Linux are the biggest ones. Of course, it should be open source. We're Red Hat. We don't really do open source. So we have a tool that works. We want it to work ideally just as well on a single machine as it does on a remote machine. And if it can work on a remote machine, why not extend it to clusters, maybe a cloud of virtual machines? And if we have such a tool, maybe to do some profiling, tell us where our program is spending most of its time. And our program being Java language program. We also want to take a step forward and do training on the JVM itself, possibly based on the results of our profiling. And then finally, we also want to do some diagnostics where we say, oh, these are what our program is doing. Here are some things that we expected it to do. Here are some things we didn't expect. This doesn't look right. So, as I mentioned briefly, we want to target open source platforms. Currently, the biggest open source virtual machine is OpenJDK, and the biggest open source platform is Linux. That doesn't mean we as a project won't accept patches for other platforms and other operating systems, but these are our main target right now. Of course, having a project doesn't mean much. We want this project to be open source. And this means having a open source approved license, and, well, in our case, that's GPL version 2 and ClassPath. We went with this license because, one, it's very similar to GPL, which basically means as long as you don't modify the thermostat itself, you can integrate it, you can use it, you don't have to share any code. Just as importantly, we do not have a contributor license agreement, so if you do want to contribute to it, we are equal partners. We, as an entity, don't dominate the project over any other. More than being an open source project, we also follow open development. This means we all follow mailing list where we do all our discussions and packages and everything. We also have a public bug tracker where you can sign up, post bugs, post patches, participate in discussions. And we also have most of our conversations and discussions on IRC, so you can talk to them anytime, see some of the developers, participators, maybe sometimes having fun, and join in. As mentioned before, everyone wants to massage to work on one machine. So as a developer, that's the machine I care most about, my machine. If my program works in my machine, I know at least it works someplace. But obviously, it's important to extend that. You want to be able to run it on a server and take a look at it. You want to extend it to a cloud, a set of virtual machines. And again, examine it with this benefit that, one, your program will not be disturbed in production, and two, you can get all the data that you expect out of it. We also want to do profiling, as I mentioned. We want to profile both the Java code and user code. This is actually output from another program called OProfile, and basically gives you counters so you can avoid the program spends most of its time. And if we could incorporate that, our serviceability tool can tell us, here's where the program is spending most of its time. If you have performance problems, here are the places you need to focus. Just as important as diagnostics, we want to be able to diagnose problems with our Java applications. There are lots of problems with applications that are often missed. Some of the more common areas include memory allocation, threads and loss, and input-output. Memory allocation, you would think isn't a problem in Java, it's garbage collected. You can allocate as much memory as you want, and you can release it whenever you feel like. But that's not strictly true. Garbage collection does have an impact on your performance. We're going to see some demos where we show exactly what that can mean, but just to give you an idea, if you hold on objects for too long, you may significantly impact the performance of the application. There are also problems in threads and logs, where you may think you have a multi-threaded application, but the two threads that are in your application may be stepping on each other's toes, really causing it to become a single-threaded application. You may have threads that are depending on logs too much, and that really means you're not getting the performance out of it that you'd expect. For diagnostic, it'd be fantastic if we could get I/O information. So if your program uses standard Java libraries, it'd be great if you could tell, oh, your program did so much I/O using servers, so much I/O using cloud, so much I/O using sockets. Probably the most interesting though is this. The diagnostic information could be something very specific to your domain. If you have a Java application server that's sending out email, all of the metrics really seem irrelevant compared to how many emails is it sending out per minute or per second. And so if we could get counters and diagnostic information that corresponds to that, that would be fantastic. And finally, if we have all this information from profiling and diagnostics, maybe, just maybe, this tool can recommend, oh, you can tune your JVM. Hotspot, as many of you may or may not know, is a complicated VM. There are a huge number of command line actions that you can use. Some of them tune which garbage collectors use, some of them tune how often it's run, some of those parameters tune what are the different memory region sizes, and it's not really simple to get it right. Especially for your application, you may be able to increase performance by picking the right set of parameters. If we have a tool that can examine everything, maybe it can offer suggestions on how to do things better.
Okay, so Omair has discussed the reasoning and motivation behind Thermostat. So now I'm going to explain a little bit about what Thermostat is today, what we hope it's supposed to be in the future, and how it works. So this diagram basically shows how Thermostat works. So we've got information from Java processes, represented by the little Duke guy, and we have information from the currently running host that the Java process is on top of. And those two sources feed into our Thermostat storage mechanism. And then we have users, who call Thermostat clients on the other end, that are pulling the information from that Thermostat storage. So some of the data collection mechanisms that we use in Thermostat, we use a lot of things-specific data, Thermostat, JMX, and also command line tools like JPS and JMap and JInfo. We also get information from /proc. So that's obviously information directly related to the host, not so much just Java. And this dotted line indicates what we'd like to extend thermostat to in the future. So that includes things like other profiling utilities like OProfile and instrumentation like BikeNet. So this is what a sample of the display in thermostat. So we gather a lot of data, and the best way we feel to represent this data is through charts. So a lot of the information that we display in the thermostat clients are rendered using J3 chart, which gives you a nice example like this, showing memory read patterns. So with thermostat, we wanted to get this whole vertical integration going. So it's one thing to just monitor the Java virtual machine, but as Omair said, you might have some custom metrics that are only applicable to your application. So we'd like to include those as well, and maybe some metrics from popular middleware. We'd also like to gather information from the operating system, like we said, like with monitoring /proc, and also some information from some minimal information from the hardware, and we've done this with NUMA integration. Another thing, analogous to the vertical integration, is we want to have horizontal integration. So we could have thermostat running on just a single machine, where all your monitoring is the processes that are running on that same machine. We'd also like to have a remote case where you can monitor Java applications running on another machine, and we'd also have it to be expandable to a cluster, where you have Java applications running an entire cluster and being able to monitor them from a single machine in a summarized format. So the design of thermostat is we have multiple of these thermostat agents, and they're very non-intrusive programs that basically just gather this information from these varieties of backends and shove them off to the thermostat storage. From there, the thermostat client, and here we've shown you the command line and the GUI, can pull this information as much as they want with having zero impact on the actual production environment itself. So this is the advantage of having the clients and agents decoupled in storage.
Now that you've heard what thermostat is, next obvious question is, where do you get it? From our homepage, of course, we have a link up there. If you go there, I'll leave this up at the end. If you go to our homepage there, and if you scroll down a bit, you can find the download where you'll see versions and releases that we've done recently. And you can get our source from there and download yourself. We don't do binary releases anymore. Of course, we're hackers though. So if there's no command line there, we won't be happy. So if you're running Linux, you can always use the package manager and install it using there. So you have install thermostat on Twitter or do the job. If you're a developer, more interesting, you can grab the source from material and build it yourself. Once you've done that, of course, you want to or maybe can succeed. Either way, at that point, you have a binary for thermostat that you can use. So how do you use it? Well, it's really simple from a user's point of view. There are two main commands that you want to run. First one, service, and second one, GUI. Service basically stores the agent and the storage that we mentioned earlier, and the GUI will start a nice GUI client that you can then use.
Okay, so we've talked a lot about thermostat. Now I'd like to ask to give you a demo of an action. Okay, so here I've just built thermostat, the latest release from Material. And I'm going to run that first command that Omair mentioned, which is starting the thermostat service, which will fire up the storage and the agent. And since we're doing this on a single machine, it makes sense to fire them up both at the same time. So we're getting a lot of output right now. This is mostly to get us in development, just to make sure we catch any bugs. So that started up. Now we'll switch over to another tab and fire up the GUI.
There it is. Okay.
So this is the thermostat view. Over here we have all of the hosts we're monitoring, and in this case we're just monitoring the one host on my laptop. So you get a basic overview of the system in the Overview tab, showing the host name, information about the processor, memory, network interfaces, and the software. Then we switch over to the Processor tab, and we get processor usage over time for the whole system. And it breaks it down by individual CPUs. It's a little cluttered, so since we just fired this up, we can say only look at the last minute, and it gives you a bit more fine-grained detail. Same thing for memory usage on the host. So all of these different lines represent total memory, free memory, used memory, swap, there's buffers as well. And this is that min integration we talked about, which this is not running on a Linux system, so it's not very interesting, but it shows you the number of hits on each node over time. So if we expand the tree, we see 2 Java processors, and one is the thermostat service, and the other is the same thermostat view. So if we look over to the CPU usage, this shows us the CPU usage for each individual Java process over time. Again, we can fine-tune the range. And this shows the garbage collection over the old and new generations over time as well. So we can see we've got some garbage collection running on new, overall it's running pretty well. This is number of classes loaded over time. So in a typical Java application, you'll see it'll ramp up quite quickly and then steady out as more and more classes get loaded. This shows the different memory regions of the heap in the JVM, and Eden being the young generation, and it goes down to the oldest, to the perm generation, which is getting removed. Also here you can trigger garbage collection, which fires off a command directly to the agent. So if we go back here, we'll see more ticks have been added for that garbage collection request we just did. This is a heap analysis pane, and it gives you basically a summary of what you just saw before. So it shows you the top line is the total heap for the JVM, and the bottom line is what you're currently using. But you can do much more with this. You can trigger a heap dump by clicking this button. And it gives you a snapshot of that process's memory at a particular point in time. So now we've got a pin here. We can double click on this. And then it comes up with a histogram of all of the objects in that snapshot. The number of instances and the size. We can sort by a number of instances. So the class with most allocation is the character array. And then we can switch over to the object browser to say we're looking for a specific class type, so we can type the hash map. There we go. And we can see we've got some hash map entries here. And this allows you to trace through the references. So if we keep tracing this back, we see we've got a hash map in a hash map array, or hash map entry array, which is referenced by a hash map, and is referenced by a hash set, and you can keep going. So if you click on any of these, you'll get some information about that object, its ID, its size, whether it's allocated on the heap. And another really cool thing is we've added this thread information pane. And because thread monitoring is a little intrusive, we disable it by default, so you have to activate it on demand. So we do that by clicking this little start recording icon here. And it gives you this nice real-time chart of the different states of each of the applications. So we can see the yellow here represents time waiting. Or sorry, just waiting. And if you go down, you can see more details about the threads in the chart. Double click. This gives you a pie chart, which gives you a percentage of time spent in each state, some VM capabilities, and some deadlock detection, which we'll show later. And this is another new thing we got recently, which is JMS notifications. So this is, oh, there we go. So whenever you get a garbage collection event happening, this will give you a nice marker in the timeline, and also other JMX notifications as well. Garbage collection has to be just when it's plugged in. So this is basically an overview of the different functionality in Thermostat, but in order to give you, I guess, some live action programs being monitored, I've got a few demos here. So the first one is just to basically stress out the CPU in cycles. So maximize it and then lower it, and then we'll see how this is affected. So we see the CPU process has just appeared here in the screen. If we go over to the CPU section, let's change it to the first few minutes. And we can see it fluctuating from maximum CPU down to like 0 CPU and back up. So this mimics exactly what the processor is designed to do. Let's see. Next. This demo program demonstrates something that just keeps on allocating memory. And a convenient way to see this is in the heat analyzer view. You can see the total, the heat capacity and the used heat lines beginning to intersect. And then all of a sudden now the heat capacity is increased as the demand slowly creeped up on what it was capable of holding. And you can see in just a second it's going to happen again. And this will continue until you get an out of memory error. So let's get rid of that. We've got another example, which is dealing with threads. So this example is supposed to be a parallel program where we have 2 threads that should be running simultaneously. So if we look at it and start thread monitoring, we've got our threads labeled thread 1 and thread 2, which you can see here. And you can see, well, thread 1 is running, which is by the blue. Thread 2 remains blocked the entire time. And now it's changed right here. So now thread 1 became blocked, while thread 2 became runnable. And as this continues, we're going to see the same thing. So this is showing you that our supposedly parallel program is actually serial, and each thread is blocking the other. So this gives you an indication that it's something you should fix. So another example is based on the dining philosopher's problem with concurrency. So this is where each philosopher needs 2 forks to eat their plate of spaghetti. And there's contention over each philosopher picking up their forks, and this illustrates the problem of deadlock. So let's run this problem. Okay, so it says philosophers are ready to dine. Press any key to begin dining. So before we do this, let's go over to Thermostat, open up the deadlock process, and under deadlock detection, we're just going to go check. No deadlock detected. So we're going to press enter. And now all 3 philosophers are holding a left fork, but now they're waiting on a right fork. So we go back to Thermostat and see what's the problem with this. And now we've got deadlock detected. So Mallory is waiting on this one reentry lock, which is actually represented by a fork. Alice is also waiting on another lock, and Bob is waiting on another lock. So they're all stuck waiting. That's why we're not getting any progress on it. So this is a way Thermostat can help you detect deadlock. All right, and we've got one final example here. So this is a rather nasty example which creates a lot of garbage collection. So it starts by allocating a very large object, and then allocating a bunch of other small objects which get garbage collected pretty much instantly. So you can see it's running kind of sluggish right now. If we go to the GC example and look at the number of garbage collectors in both the old generation and new generation, we can see that the garbage collector is getting invoked quite a lot. And particularly this is bad on the old generation, because the old generation uses a garbage collector algorithm that's called a stop the world algorithm. What this does is that when the garbage collector is running, it completely halts your program. So obviously that's very bad for performance. So you want to minimize the amount of garbage collectors I have on the old generation. So if we were to run this, old generation meaning long-lived objects that either haven't fit into the new generation or have been around long enough to get promoted onto the old generation.
Just to elaborate on that, OpenData Hot Button in fact uses a generational memory allocation strategy. So what it does, it has a number of pools for allocating memory. Once you create a new object, it'll put it on a pool for new objects. And once that object has survived for a few garbage collection cycles, it gets promoted to a new generation. And it only triggers garbage collection on older generations when it absolutely has to.
So, one of the things that someone mentioned you wanted to do with Thermostat is in the future be able to provide suggestions for tuning the gradient. And this is just one of those possible tunings that will lead to much better performance. So this is increasing the size of the young generation, which allows the objects to continue to be allocated in the young generation and not have to be moved to the old generation. So if we run this with an increased young generation size, we can now see it's running much smoother. And if we go back to our GC example, there's still some garbage collection happening in the new generation, but absolutely nothing happening in the old generation. And that's why the program is running much smoother. Okay, so that's a demonstration of Thermostat's basic functionality. So let's continue on with the slides.
So now you've seen Thermostat. You saw some of the cool things that you do, and you might be wondering, if you're sitting here at an open source conference, how you contributed. It's really simple. The first step to contributing, of course, is using it. Once you use it, like all other products, you're going to see there are bugs. There are features that you want to implement that aren't there, and there are patches that you possibly can write for stuff that you see in Thermostat. And submitting patches and bugs and everything is pretty simple. You submit them all to our Bugzilla. And for patches specifically, you can just pull out a repository, create a disk patch, and send it either to our mailing list or our bug tracker to review patches in both places. This is the same process the full-time developers on Thermostat use, and anybody else can use the exact same process. Well, contributing to the core Thermostat is one thing, but sometimes you want to extend Thermostat to do things we didn't think that Thermostat really could do. An example of that would be a Java server that's sending out email that I referred to earlier. In that case, you want to add a new feature to Thermostat, but really, there's no place that's trained for something very specific here. And in that case, what you want to do is to extend Thermostat. How do you extend Thermostat? You extend Thermostat through plugins. In Thermostat, really everything is a plugin. A lot of stuff that you created earlier, those are just plugins. They ship with base Thermostat, but they're really just plugins. And you can write your own. Core Thermostat really can't differentiate between Thermostat supplied plugins and non-Thermostat plugins. In fact, there is only one API, and everything that ships with Thermostat uses that same API. All the external plugins would use that same API too. So what exactly can plugins do? Well, everything we showed earlier. They can introduce new data collection methods. I talked earlier about, Elliot talked earlier about how an agent can collect data and send it to the storage. If you expand an agent, you see that it consists of a core and a bunch of backends. Each backend is essentially that plugin. In this case, using two different backends, one collects data from /proc, uses the core API to send it to storage. Backend 2 collects data from the Thermostat and uses the core API to send it to storage. You can add a third backend that collects data maybe from your custom application and keeps it in storage. Plugins can also add new commands. We showed the GUI and the service commands, Thermostat actually transfers a whole other bunch of command line tools too. So if you're a command line junkie, there's some stuff there too. And a lot of the commands that actually come with Thermostat are plugins I've highlighted a few. These are plugins, they ship with Thermostat, but they're external plugins, really, and they contribute commands to the command line user. Just as awesome, right? Plugins can contribute UI elements. So in this heat analyzer there, or heat analyzer tab we showed earlier, it's a separate thing in here. You can't tell it's not really part of Thermostat, but it's a plugin into the GUI, actually this GUI element, so you can write your own plugin that adds more GUI elements that is appropriate for your application, maybe.
And every single one of those tags are actually plugins. So
how do you create a custom plugin? It's not very complicated, especially compared to some of the other plugins. Like we have an API, you code against it, you build it, you write one file that describes the plugin so our Thermostat knows how to load the plugin, and then you put all those files in the right place where Thermostat expects to find it, and we'll load it up when we next start. Let's go into those in a little more detail. So our API is basically a Java API. One example is in the backend. So you write a class that extends base backend, and now your class is using the Thermostat API. You can do whatever you want, just follow the semantics of the methods you would like you to implement. Once you have your code, you can build it. You can go over to your find custom. You just name it. It's not a big deal. The only requirement is it has to be a valid OSGI module. Thermostat uses OSGI modules to build its extensibility layer. And once you have that OSGI module, you need one more thing, which is a plugin descriptor file. This file describes your plugin. Elliot will go into more detail about the content of this file, but it's an XML file, and it requires a certain format. Once you have this file, you put all your OSGI bundles in the XML file, and this will next have the location inside Thermostat, and on next run of Thermostat, it will load up the plugin and be good to go.
All right. So I'm going to show you some of this awesome plugin functionality we have in Thermostat. So first I'm just going to kill this. All right. So the first one we're going to do is a simple contribution to the Thermostat command line. So it's called the kernel command line plugin. We look inside, and we've got three main components of it. We've got an agent, which contributes a new backend, which basically grabs the command line of the running kernel and puts it into Thermostat storage. We have a storage module, which basically gives a representation of that kernel command line that can be read by the client. And we've got the client component, which actually displays it to the user. And the plugin descriptor file that Omair was talking about is this XML file. So we have a commands element, and this is used for contributing new commands to Thermostat. The new command that we're including in this case is the kernel command line. You can give a nice description that will show up in the help in Thermostat. You can specify command line options in both long and short. In this case, it doesn't do anything, but we just wanted to demonstrate that this functionality is available. You can specify the environments which this command is valid for. So in Thermostat, we have a command line utility, but we also have an interactive shell. So you can choose either one or both of these environments for your new command. And then finally, you specify each individual bundle, OSGI bundle, that is to be included and activated for this command. So in this case, we have our client command line interface, and we have the storage edition as well. And then a whole bunch of dependent bundles that are provided by Thermostat. We list them the same way. And then we have an extension, which is for existing command line. You can get your new plugin bundles to activate when this command is run. So when you run the Thermostat agent, which is part of the Thermostat service, it also loads our agent bundle, which includes our new backend and the associated storage component. So that's all you have to define for Thermostat plugin. We can easily build it. We use Maven for ours as well. And there's not much to this, so we'll build quite quickly. All right. Then all we have to do is copy the resulting jars and that XML file over into our Thermostat instance. So we've just got a handy script for doing that. So it's just copy the files. Sorry, it's a bit long. So now we go up to our Thermostat image, which is our basically Thermostat home directory. We look inside, and under plugins, we see a lot of the same functionality we have already. So like host CPU, host memory, VM CPU, those are all those things I showed you already. But now we also have this kernel command line, which is what we just added in. So we try running the Thermostat service again. And now you can see this line here, it's added our new backend for the kernel command line. So now this is running part of Thermostat. And now if we run the Thermostat help from the command line, we see now we have kernel command line included along with the rest of the Thermostat commands. So let's just try executing this. And here it is. It's printed out the command line that's run, the kernel that is running on my machine right now. So that's a very simple way to extend Thermostat for any sort of functionality you want. So that was one demo. Now I'd like to show you another one, which actually is Thermostat GUI. So again, we have the same components. So we've got a custom backend, which is included in the agent bundle. We've got a storage edition, which is called common in this case. But instead of a command line client edition, we have a GUI client edition instead. The Thermostat plugin.xml looks very similar, although it's much shorter because we're not adding a new command in this case. We're just extending the GUI. So we'll build this as well. And this plugin is an example of monitoring some application-specific metric that only you care about. And for this, we have a special custom program that specifically outputs this metric that we're looking for. So we built that. We'll install it the same way. Run the Thermostat service again. No need to build Thermostat. And now you can see this line here. We've added our backend that is contributed by this plugin, which is just called custom. We'll probably have a better name for it. And now we'll fire up the Thermostat GUI. And look at one of the Java processes. And now we have this new custom tab here. And it's not really showing anything right now, but that's because this is Thermostat itself, so it's not outputting any specific custom metrics we're looking for. So let's go to our custom program and run that. And if we go back to the Thermostat GUI, now we can see we're getting some of our custom metrics output from this specific program. So this could be something like number of emails sent per second on an email server. So it's very easy to extend Thermostat to monitor whatever custom metric you're looking at. So now we're going to talk about what's been a big deal for us over the past year, and that's getting to our 1.0 release of Thermostat. So the first thing is, what is a 1.0 release? What's so special about it? Well, every project has their own concept of what needs to go into a 1.0 release. Ours hasn't been so much on getting the features in there, but getting the proper base and building blocks for people in order to make those features that they really care about. So Omair talked about our original plan we've had, which includes targeting OpenJDK, being open source, working on a cluster, and giving you diagnostics, tuning, and profiling. Well, for 1.0, we have to scale it back a little bit. We've gotten rid of the tuning and profiling after we get our 1.0 release. So all the things you've seen so far are monitoring and diagnostics. But what we've worked on really hard is the security aspect of Thermostat. So you can see here we've got the Thermostat agents on one side, the storage, and the users on the other. And we put in all of these security mechanisms in order to make sure that what is sent to the storage and what is retrieved by the users is done securely. So we've done this by making all communications go over SSL. We've also done it by integrating JAS, which is the Java Authentication and Authorization Service. So this allows you to define custom roles for users, saying that, okay, this person is allowed to trigger a heat map of this data, and this person's not allowed to read it, because hey, it might be a bank with very sensitive information, and we don't want anybody to be able to read that. And another thing we've done is implemented prepared statements for both reads and writes in Thermostat. So this allows you to verify, for Thermostat to verify that the queries and writes that it gets are valid, and you don't get anything that says like where 1 equals 1, and get all of the results back. Another thing we focused on is stability of Thermostat. So this is doing tons of bug fixing and making sure that the features are great. And another thing that has been really big is API stability. So this is our plugin infrastructure. This is making sure that when we got the 1.0 release out, it's ready for consumption, and people can start writing their Thermostat plugins and it'll work. And our 1.0 release is due really soon, any day now. all the members on the Thermostat team are working on the last important issues to get done, and as soon as that's done, we're going to cut our 1.0 release.
Now that we're about to release the 1.0, it makes sense to take a look back and see some of the lessons we've learned while working on Thermostat project. Our hope is viewers can also learn something that you find useful. One of the first things that we learned is that the best way to test an API is to use it. When we wrote our API, we had unit tests. We thought they were good enough. We thought we had everything we needed. And then we started writing custom plugins, and then we realized, oh, we don't have that implemented, we don't have this implemented, we have that broken, we don't have that working correctly. And so I really want to emphasize it. If you're ever writing a plugin mechanism, if you're ever trying to write an application that's supposed to be extensible, exercise it. Write custom plugins, you'll test out the API like you've never, ever had. Another lesson that we learned, well, first a little bit about our development practice. We do work in the open community, but we do sort of try to practice as specifically Scrum. So we'll have daily Scrum meetings on our IRC channel and so on. And while we have tried to try agile technology, we found out that it doesn't really always work. There are downsides to it, there's some benefits of it too. Some of the things we found awesome was that during our daily meetings, we can all sync up. We all know what's going on. We can all share our problems and figure out what we want to do next. But there are lots of problems in Agile too. Some of the problems include the fact that if what you're working on isn't straightforward to implement, if it takes longer than, say, a week or two, it doesn't really fit in the Agile schedule, then you have a bit of a problem because you're not supposed to ever use features or ever have half-completed features. So it doesn't really fit in that same style. Communication is sometimes also a problem with Agile, especially because it encourages that we have daily meetings at the beginning of the day. Well, with a distributed team across the entire globe, that's not really possible. If we have a meeting in the morning, it'd be midnight for some of us. So really, Agile, there are lots of good things about it, things like unit tests that highly encourage everyone to try. But then there are other things that make it so you don't want to use Agile unmodified. You probably want to tune it and tweak it to apply to your team and your development practice. And finally, possibly the most important lesson that I've learned is that there's no substitute for user testing. As I said, we do Agile. We have unit tests all over. We wrote integration tests. We even had dedicated CD folks write tests to exercise all of our UI elements. And then we participated in the Fedora test day, where we had random people come in and try to use our product. And then we found out, oh, here's one path we never thought about. And it turns out what users do is pretty unexpected. Users will try to use features in a way you haven't. They'll try to exercise them more thoroughly. They'll try them in weird combinations. They'll try unsupported ways to do things. Basically, if you haven't thought about it, the users will try it. And so it's really very important to do user testing to get a solid product. Sometimes it seems like users are finding too many problems, too many flaws, and I think that's a good thing. You really want to understand that the users are at the end of the day who are going to use your product. So if they're finding problems, better fix that. And hopefully, by taking this feedback from users, we've actually made Thermostat a better project. We've tried to integrate all the different aspects of our serviceability tool. We've tried to gather feedback from users to try making it awesome. But at the end of the day, it's really what it is, and we try to make it great. But before I end this talk here, I have a challenge for you all. You all saw what Thermostat is, what it can do. Now, my challenge is that you want to take a minute or two and think about it. Are you a Java developer? Are you running into performance problems? Is there any part of this tool that is applicable to you? If so, try it out. If you're looking to participate in an open source project, here's an awesome project that you might want to help in. And even if you're none of those, if you are just a developer or an IT guy, is there some idea in this that you are kind of interesting? Something you would adopt, some methodology, some policy, or something that's suitable for your project? And if you can do that, then I think our talk here has been a great success. I want to thank you all for listening. If there are any questions, I'd be happy to take them. But first, I just want to point out our website is up here. You'll find links to our IRC, mailing list, Mozilla, and everything.
And please do contact us.
But thank you very much on behalf of Seneca. Please come back another time. Should iterate in the CDOT, people doing programming work down there, we've been using Agile for now, and we're considering this Scrum idea as well. For what sound like very similar regions. It works very well in some situations, but if you're in a kind of development where your project is moving or your scope is coming in quite rapidly, you just can't keep up. Anyway, thank you very much, guys.
Thank you.
Please feel free to ask questions, but if don't got the outside of it.
So our main development environment is Eclipse. So we use Eclipse for building and everything. Exactly, exactly. Command line makes it a little more hard to actually do development. On the other hand, the main integration in Eclipse has a few problems. So if you really just want to build it for like final testing, I'd recommend using command line moving to build Eclipse had a few integration problems there.
Yeah, it's the same thing with me. I do all my development on Thermostat within Eclipse, and then when it comes to build, I'll build up to my line.
So I understand very different. Not be realistic.
I know as a project, I don't think we ever talked about supporting Railroad.
No.
Did I miss that discussion?
No, I don't think we did. We're all big fans of Android as well. But yeah, right now our main target is to get it working and well on OpenJDK.
Sorry, I just want to make one main point there. I think these sort of things make a lot more sense when you're running it in a production environment. Android, I assume you can just stop your application. Like, you won't ever have mission critical applications that you can't stop, or that you want to keep as one extreme one that I think I would use your example. So maybe it's not the exact same in this case. So it's not, I mean, if there are people who want to contribute practices thermostats to support that, we're happily accept it. It's just not something we're doing right now.
Okay, so just one more question, and please ask me to move so that the next item.
You maybe plug-in auditory or people can do your plug-in to a simple block, or if you
I don't think we ever thought about having those other plugins.
I mean, like, obviously anything that is not overly specific to you is also going to run the thermostat itself. But if it is like specific or too specific to get it right in the thermostat, that would be a good idea.
Yeah, it sounds like a good idea. We haven't thought about it.
Mm-hmm.
Okay, so just a reminder. So we've got characters at the end.